Hello. This is my second part because it's over. I'm still on the design guide. We were just want to finish this. We were doing this here, and we just put all the decoupling capacitors in, and the quite funny switching power supply that was quite fussy. So it's the exact clone of what it should be in the design guide. Now I am. We were reading through input supply. We've done that. Decoupling capacitors. Now it's the flash memory. So this is where the main firmware is held, the custom firmware that you'd write for this device. On the RP2350 and 2040, and I think the ESP32 as well, the flash memory is actually a separate chip. A QSPI, quad SPI interface. Just put my phone on mute. So I'll read it. It says, in order to be able to store program code which the RP2350 can boot and run from, we need to use a flash memory, specifically a quad SPI flash memory. The device chosen here is the blah blah blah, blah device U3 in figure 8, which is a 128 megabit chip, 16 megabytes. This is the largest memory size that the 2350 can support. If your particular application doesn't need that much storage, then the smaller chip could be used instead. I'm going to use the largest size because in our design I'd quite like it so you could run multiple codes at once or store them side by side. I'm also wondering whether you could load programs from SD card. That's going to come much later. As this data bus can be quite high frequency and is regularly in use, the QSPI pins of the 2350 should be wired directly to the flash, and you should use short connections to maintain signal integrity and also to reduce crosstalk in surrounding circuits. Crosstalk is where signals in one circuit net can introduce unwanted voltages in the neighbouring circuit, potentially causing errors to occur. The QSPI SS signal is a special case. It's connected to the flash directly, but also has two resistors connected to it. The first, R1, is the pull-up, which is this one here, to the 3.3 volt supply. The flash memory requires the chip select input to be the same voltage as its own 3.3 volt supply as the device is powered up, otherwise it does not function correctly. When the RP2350 is powered up, its QSPI SS pin will automatically default to pull up, but there is a short period of time during switching on where the state of QSPI SS cannot be guaranteed. The addition of pull-up resistor is that requirement and will always be satisfied. The R1 is marked do not fit on the schematic, as we have found that they're not really needed. That with this particular flash size, the pull-up is unnecessary. So it probably ignores that brief period of time whilst everything's starting up, and it's fine. But there could be a flash chip that will do funny things if it's not pulled up straight away. However, this is what it says. However, in a different flash is used, it may become important to insert the 10k resistor here. So it's a just in case. I'll leave it in. So that's this one. Value is DNF. It's better to go 10k and then go do not populate, like that. This was introduced in KiCad 8, I think. You can there's a do not populate property, and you end up with a crossed out. I'm doing the same to the PS RAM because I know it's the same. The second resistor, R6, is a 1K resistor connected to the push button SW1 USB boot. Yeah. This is because the QSPI SS pin is used as a boot strap. RP2350 checks the value of this I/O during a boot sequence, and if it's not found to be logic 0, as in this, and if it's found to be logic 0, so the button's on, then the RP2350 reverts to the boot cell mode. That's the internal boot code, where RP2350 presents itself as a USB mass storage device, and code can be copied directly to it. If we simply press the button, we will pull QSPI SS pin to ground, and the device is then subsequently reset by toggling the run pin. The RP2350 will restart in boot cell mode instead of attempting to run the contents of the flash. These resistors R1, R6, R9 and R10 also should be placed close to the flash chip so to avoid the additional lengths. So we've got QSPI SS going to USB boot. Then I've got USB boots separately in our schematic. Why does it have GPI? Oh yeah. So that's do not fit, but we are going to fit that. It's probably going to explain this now. All of the above specifically applies to the RP2350, which has no internal flash. The RP2354 has a flash, so the external memory is not of course required, so U3 can be safely removed from the schematic or simply left unpopulated. In either these cases, we still want to keep USB boot switch connected to QSPI SS, so we can still enter the mode. RP2350X now supports a second memory device using the same QSPI pins, with a GPI providing additional chip select. So if we are using RP2354, then we could use U3 as a secondary flash, or even replace it with the PS RAM device. In order to do this, we need to disconnect QSPI SS from U3 and instead connect it to a suitable GPIO instead. The nearest GPIO capable of being a chip select pin is GPIO 0. So by removing the 0 ohm from R10 and fitting it to R9, we can now access U3 in addition to the on-chip flash. In order to develop this feature, we need to have two external memory devices, so the flashless RP23 can benefit from the larger of the two minimal boards. To be able to use this device, it will obviously have to be populated as well. But the A3 Metro has both. So what have they done that's different? Because if you look at this, I won't show it, but if you look at this in the board file, this is the same footprint. They're just sat on top of each other, which is not what we want. We want to have both accessible. So I'm not completely sure how it works yet, but it looks like if if you see in this, it looks like, I know that's just, yeah, it looks like they connect them to the same QSBI bus, but the chip select is different. So they still have the pull-ups, do not fit pull-ups. We want that to be 100N, but we don't. They've designed it so you can have that or that. You can have the flash or the PSRAM, and you can only have the PSRAM if your chip is the one with the internal flash, but we don't want that. We want it more like the Adafruit configuration, so we've got the pull-up. And then the QSBI chip select, that's its own dedicated pin. Or is it on a GPIO? Where is it? There's the QSBI. They're dedicated, which is here. The QSBI SS. But what they've done, they're using some kind of diode. USB boot. What's USB boot? That's interesting. I wonder what that's for. MT. The PSRAM chip select is there. And is that, have they put it on GPIO 0? No. Where have they put it? They've put it on GPIO 47. Just copy that. This is a lot simpler actually. USB boot. Overview. Anything that mentions a USB boot. It seems like USB boot. Optional boot signaling was protected over OTP storage. Boot signing. No, that's the chip feature. That's the security stuff. There's nothing here about that. There's a test point. It's got a test point on USB boot. It seems to be able to reboot itself, but why? So my drink. Say the Metro. Might have to just move on from this. This is the RP2040 version. No. I wonder what that is. Some feature. Might be if it's. Sorry. Got water everywhere. Pico boot. I wonder if it's something to do with loading from over USB. Not sure. I have to find out what that is. But we've got these two pull-ups. We've got the QSBIs are connected to each other to the same input port, and then you have two separate chip select pins. And I think I'll use the same chip select pin as on the Metro. Just because that's a setup where it's used in parallel with the RAM. The flash and the RAM are used in parallel. And that is used on here it is, pin GPIO 47. So I'll just move that. I'll copy that. No, that's clock. This. And I'll delete that. And I'll put it onto GPIO 47. Now it's ADC. I might just label it as well. the chip select. Just so I know what it is. We don't need this because this is for if they're on this. It's for the yeah. Then we don't need these or this. Yeah, you don't connect the chip select directly to QSPI chip select. Yes, you do. But we don't need that. Because that's the, again, choosing between. Keycard. You can see on a different grid. There was something funny that happened between keycard 7 and 8 and 9 where the grid went funny. I don't know why. But I've got USB boot here. Oh yeah. It's called USB boot, not chip select. I quite like showing it as, let's call it QSPI SS. Should we call it USB boot? Let's call it QSPI SS. I want to make it negative. Inverting. What's that? I can't remember the syntax. Oh, here's the syntax help. Yeah, that's right. So that's the same as these. This mouse. So the idea is that oh, there's meant to be a resistor. Oh. So you need a resistor here. Why is that again? Because why do you need a resistor there again? I can't remember why. Does it connect to two places? So 1K resistor. Second resistor, 1K, is connected to the push button USB boot. This is because BI pin uses a bootstrap. Why does there need to be a resistor though? I can't remember why. Because surely it can just be connected straight to the pin and pulled to ground. There was a reason. Anyway, can't dwell on that. So I also need to work out what the hell this USB boot connection is for. It seems so it can reboot itself, because it goes from a GPIO. I wonder if it's in the bootloader of CircuitPython or something. I don't know. Don't know if I should put it in or not. I won't for now. I'll come back to that later. I'll do a bit of research off the video. Okay, spots flash it. Let's just skip past that. So we're just going to use the one. Now this is important. Crystal oscillator. Strictly speaking, the RP2350 doesn't actually require an external clock source, as it has its own internal oscillator. However, as the frequency of this internal oscillator is not well defined or controlled, varying from chip to chip as well as with different supply voltages and temperatures, it is recommended to use a stable sorry, I got distracted. Stable external frequency source. Applications which rely on exact frequencies are not possible without external frequency source, USB being a prime example. Providing an external frequency source can be done in two ways: either providing a clock source from a CMOS output, square wave, into the X-in pin, or by using a 12 MHz crystal connected between X-in and X-out. Using the crystal is the preferred option here, as they are both relatively cheap and very accurate. The chosen crystal for this design is this one. It is the same 12 MHz crystals used on the Pico and the RP Pico 2. We highly recommend using this crystal along with accompanying circuitry to ensure that the clock starts frequency under all conditions. The crystal has a 30 parts per million frequency tolerance, which should be good enough for most applications, along with frequency tolerance of 30 plus minus 30 ppm. It has a maximum ESR of 50 ohms and load capacitance of 10 picofarads, both of which had a bearing choice of the company components. For a crystal to oscillate at the desired frequency, the manufacturer specifies a load capacitance that needs for it to do so, and in this case it is 10 picofarads. This load capacitance is achieved by placing two capacitors of equal value on each side of the crystal, C3 and C4. From the crystal's point of view, these capacitors are connected in series between the two terminals. Basic circuit theory tells us that they can bind to give a capacitance of this, and as C3 equals C4, then it's simply C3 divided by 2. In this example we've used 15 picofarad capacitors, so the series combination is 7.5 picofarads. In addition to its internal load capacitance, we must also add the value for unintentional data extra capacitance or parasitic capacitance that we get from the PCB tracks and the X-in and X-out pins of the RP2350. We'll assume the value of 3 picofarads for this, and the capacitance is in parallel to C3 and C4. We simply add this to give a total capacitance of 10.5 picofarads, which is close enough to the target of 10 picofarads. As you see, the parasitic capacitance of the PCB traces are a factor Therefore we must keep them small so we do not upset the crystal and stop it oscillating. Indeed, try and keep these as short as possible. The second consideration is the maximum ESR of the crystal. We've opted for a device with a maximum of 50 ohms, as we found that along with a 1K series resistor is a good value to prevent the crystal from being overdriven and damaged when using IOVDD at the level of 3.3. However, if IOVDD is less than 3.3, then the drive current in X and X out is reduced, and you will find that the amplitude of the crystal is lower or may even not oscillate at all. In this case, a smaller value of series resistor will be needed. Any deviation from the crystal circuit shown here or with an IOVDD level other than 3.3 volts will require extensive testing. So we'll just use the standard crystal. When I designed the RP2040 before, I used my own crystal and it was okay. But now it seems like all the parts are in JLC anyway, so it should be fine and lower risk to use the layout. There's no image of the layout. So we'll just have to copy it. For just a minute. Alright, I'm going to stop it here. I'll do some more tomorrow. Okay. Bye.